So we're starting our second lecture for this week. I felt that the last lecture somehow I lost you or you lost me, whatever the right direction is. So let us first repeat a little bit of the material that was covered on Sunday. So it's actually quite important. So what have we seen? First of all, we derived stability relations, right? Second. Right, turn it on. So first, we derived stability relations. If we have two systems and they are in equilibrium with each other, okay, so the pressure of system A equals to the pressure of system B, the temperature of pressure as system A equals to the temperature of system B, and the chemical potential of system A equals to the chemical potential of system B. Now, how we obtain these relations? What we have done is we expanded the energy, okay, up to a first derivative. So it's a first order expansion of the energy. We assume that we have two systems, A and B. Okay. We assume that we can have some sort of a perturbation by imposing internal constraint. Okay. And then we looked on what happens to the different properties or the different energies of system A and system B, while keeping in mind the variational principle that delta E was larger than 0. Okay? Now, what I mean by first order expansion, second order expansion, and etc., I'm basically saying the following, that a change in the energy, okay, is the first order expansion, some small changes, plus the second order expansion. Okay. What is this first and second order expansion? It's basically a Taylor expansion of the following form. So delta E, it's already a change. Let's write it down like this. So it's E equals, or E plus, mean by E plus or E prime, minus E0 equals E0 plus dE to ds delta S plus 1/2 d squared E to ds squared delta S squared. Okay? If I assume that E is a simple functional of the entropy, okay, this is going to be the Taylor expansion of this function. Now, the thing that we have done on Sunday is exactly to use the first order expansion of the energy and to take only the derivative with respect to either energy or either entropy or volume or the number of moles that we have in the system. Okay? And what we have seen that those relations has to be always satisfied, right? And delta E, okay, and delta E, which is dE to ds delta S, is always 0. In the specific case that we have a general entropy that is kept constant, the general volume that is kept constant, and the general number of particles that is kept constant. They can only switch particles from one to another. They can switch entropy from one to another. They can switch volume. Okay? But the total entropy and volume and the number of particles is kept constant. Okay? So those relations were obtained when we neglected the second order and we used only this part. Right? This part basically says that we are at a minima. Right? This is why it has to be 0. Additional relations were obtained when we use the second order expansion, right? What was the second order expansion? We said, well, delta E is delta E plus delta E squared. This guy equals to 0 according to those relations. And this delta E squared, we use the second order derivative of the energy with respect to entropy. Okay? And we use the fact that delta S is now to the second power, is taken to the second power, so it's a positive quantity. What we have obtained are additional set of stability relations. It was, we have proven that CV is greater than 0. Okay? This is what we have seen. Now here, questions? So here we used this variational property, that the energy, if we perform or imposing internal constraint, or the system attains some sort of internal fluctuations, the energy always grows. Okay? We can do the same thing, but not for the energy, but for a quantity like enthalpy. Okay? So enthalpy equals E plus PV. Okay? For enthalpy, there's also a variational principle that fluctuations only give rise to the enthalpy. Okay? So delta H is also greater than 0. Okay? When we use now the first order derivative and the second order derivative of enthalpy with respect to volume, for example, we will obtain, or pressure, I'm sorry, with volume, we will obtain that Cp is greater than 0. Okay? We can repeat all the derivation that we have performed on Sunday, but for enthalpy, this is an additional stability relation that we will get. Okay? If we will do this trick again, but for, let's see, Helmholtz free energy, which is A equals E minus Ts. Again, for A, there is a variational principle. At equilibrium, A is in its minima. So delta A is greater than 0. Okay? Again, we expand A with respect to changes in volume. All right? We use the first order derivative, obtain something. We use the second order derivative. And what we obtain over here is that minus dp to dv, while keeping everything else constant, t and n, is greater than 0. Okay. This is all actually related to some measurable quantity that is called isothermal compressibility. Kappa, which is minus 1 over v dp to dv, keeping t and n constant, and it's greater than 0. Those are stability relations. They are based on the variational principles, and they depend, well, there are several of them. Basically, actually depends on what kind of function you're expanding. You can expand energy, obtain this guy. You can expand enthalpy, obtain this relation. You can expand Helmholtz, etc., etc., etc. In general, there is a rule. You take a function of state, you expand it up to a second order, right? And then you obtain some sort of a relation. And it will always hold. Now, for our purposes, we only need this guy, and this guy, and that guy. But, as you can see, there is a huge number of them. Use your favorite function of state, expand it to the second order, and you will obtain your own stability relation. Is it important? It depends on the system. Now, after deriving those stability relations, you're too quiet today. You should ask something. No? What?
How are you?
How are I'm fine, thank you. Thank you, Yoni, I'm fine. How are you, Yoni?
Surviving.
Thanks. Okay. That's actually been helpful. Okay, so where we went next? We went to phase transitions. Okay. If I'm losing you, you're losing me, please ask something or just state the fact. So phase transitions, even in Hebrew. Now, phase transitions. We are all familiar with the fact that when we boil water or heat up water, let's see. So this is our chamber. Here is water. We heat it up, okay? We heat it up. After a while, we will start to see vapor coming out of this water, right? Now, it's not that we created air or it came out of nowhere. Those are basically molecules that were previously watery and now they are airy, okay? Water, vapor. Basically, those are the same molecules that previously were water, now they vapor. Okay? It's the same molecules, it's not something different that happened over there. What we call this phenomena, we call this a phase transition. So there was a phase or a state of matter that was liquid. We heated it up, okay, we increased temperature, or we pressured, released the pressure, or we changed the pressure somehow, and then instead of water, we obtained vapor. Okay? Now, under specific conditions, we can actually keep them together. We can close it up, and part of our system will be in phase of water. The other part of our system will be in the phase of vapor. Okay? Now, if we look closely, we would see that the specific volume, or the density, if we like to say it in this way, is very different in water and in vapor. So they coexist together. We heated the system, some of the system is water, some of the system is vapor. There was a phase transition from liquid to gas, right? Liquid and gas. There was a phase transition. And now they coexist somehow, right? We will discuss this coexistence till the end of this lecture. Now, I want to understand something about this transition from liquid to gas. Why? Because if I look on the density of the material, I see that the density of the material is much more denser when it's in its liquid phase than when it is in its gaseous phase, right? So this is what I see. I see that although they are coexisting one with each other, okay, there was a huge jump, not huge, there was a big jump of density or specific volume, okay, when the part of the molecules turned from water to vapor. Okay, how do you see it? You have a kettle, you heat it up, you start to see those bubbles. Right, the bubbles are the same water molecules that were there before. They haven't arrived here from beneath the kettle. Okay? And basically, those molecules have much larger volume. And that's it. But this occurred suddenly. If you see suddenly, a bubble appears in the kettle. By the way, this is a very ancient technique of measuring the temperature. The size of the bubbles describes to you very exactly what is the temperature of the water under 1 atmosphere pressure. All right, so I see this change as a jump in volume of the molecules, and I want to use this fact in order to properly describe or find at least a quantity that will describe to me this transition from gas to liquid. Why it's important? Because all what we have assumed so far was some very nice continuous transformation of one equilibrium state to another. Then from this additional equilibrium state to another, everything was continuous. Suddenly we see something that happens abruptly. Interesting. Okay. So what do we do? Questions? No? So what do we do? What quantity we have that actually can display to us this abrupt change in volume or in entropy, right? Because now we know what is the difference between vapor and water. The same molecules that are basically moving much more faster. The number of neighbors that they encounter on the way basically is very small. This is gas. In water, all the molecules move together one with each other. Okay? So the entropy is also performing some sort of a jump. This is what we know so far. But from experiment, I can see that there is a jump in volume. For the entropy, I can say there is a jump in specific heat or whatever. Okay, so what quantity that I can use in order to describe this transition? What? Sorry? CV, yes, but some other guess? Not temperature. Temperature is the same. You see, the temperature of the water and the vapor is exactly the same. They are in equilibrium. Okay, so all those criteria, okay, for stability of two systems holds. Okay, I close the system up, they coexist with each other. You can say that those are two different systems in equilibrium. The temperatures are exactly the same, the pressure is exactly the same, and there is a third quantity, chemical potential. Okay, so the chemical potential is also the same, and this is the interesting quantity. Why? First, I don't really understand what it is. Okay. B, there is a nice equation that we've derived previously. Okay, Gibbs-duhem equation. What is this Gibbs-duhem equation? 0 equals S dt minus V dP plus N d mu. How does it help us? Well, d mu is S divided by N dt with a minus sign plus V divided by N dP. V divided by N is simply density, okay? And S divided by N is entropy per molecule, or per mole. Now, from this equation, I understand that mu, okay, is a function of T and P. So if I have stability relation says what? That the temperatures are the same, the pressures are the same, and the chemical potentials are the same. But the chemical potentials are defined and dictated by the values of T and the values of P. Moreover, from this equation I see what is the derivative of mu with respect to temperature is minus S divided by N. And what is the derivative of the chemical potential with respect to pressure? d mu dP equals V divided by N. Here I will say that here I'm keeping pressure constant, and here I'm keeping temperature constant. Now this is what I wanted to find, this equation over here. Why? Well, you see, I know that the density is jumping. The density of water is much higher than the density of gas. Okay. What it means that if the density jumps abruptly from one point to another, the derivative of mu, okay, is discontinuous. So now I start to understand something. First of all, those two systems are coexist with each other. This is an equilibrium. So the temperature and the pressure is the same. the chemical potential is the same, but something interesting happens to the derivatives of the chemical potential, and it is that the derivatives are discontinuous. So when I would try to describe the system by using the chemical potential, I must obtain some sort of a function or behavior of a chemical potential that will give rise to this abrupt jump in the derivative of the chemical potential. Okay, so, and this is the plot that we had on Sunday. So if this T, this P, and this is mu, oh, I have more markers over here. So mu is a function of two variables, T and P. So it's a surface in three-dimensional space. Okay. And what we can say that part of this function, okay, will describe a gas. For some other parameters of T and P, the chemical potential will be describing liquid. Because this is liquid. When we say that the gas and the liquid coexist together in the same system, this transition then must occur on this line, okay, that separates the behavior of the gaseous state and the behavior of the liquid state. This line over here, it has a name, it's termed a coexistence line. Okay. So when I'm heating up the system, it can go from gas to liquid or the other way around, or I can change or vary the pressure. There is a transition. Exactly at the transition, and this is the interesting point, because going from one point on this liquid to another point of this liquid is boring. It's the same liquid, okay? And going from one point on this gaseous state to another point on this gaseous state is again boring. When it's maybe a little bit less boring, when we cross over, okay, this coexistence lines, and we have a different behavior. Okay? It's nice. We have water, we have vapor. Okay, we can cool it down and we can have liquid. Yes?
So in this example, in this system, the delta mu should stay 0 also, right?
Yep. On this coexistent line, you see it's continuous. Mu is absolutely continuous. Nothing, if you inspect mu, nothing really happened. You have to inspect the derivatives of mu. No. No.
But I can see in this equation that if the mu is 0, so the derivative should grow by the same amount.
It depends on what you exactly change, right? You can keep the pressure constant, okay, and change the temperature, or the other way around, right? If you can't, so they are not exactly the same, and we will see this. Any other questions?
Yeah. What happens to this coexistence line? Is the velocity of the molecular?
So on molecular scale, I am a molecule, and I have a lot of different other molecules, and I'm in water in the liquid phase. Okay, we all move together. Okay, right? In the coexistence line itself, or a little bit below, we're in the water phase. A little bit above, I already lost all of my friends. I'm a gas. So I look around myself and I don't see anyone. Okay? And if I understand your question correct, what exactly happens on this line itself to the molecule. So there we will see there are two types of phase transitions. One type of a phase transition depends where I came from. If I'm coming from a gaseous state, on this specific line I will still be in a gas. I'll cross a little bit more and all the system abruptly at once will turn into water. Okay? Or the other way around, I'm coming from water, right? I'm coming from water, I'm still in a watery phase. On this coexistent line, okay, on this coexistent line, I'm still in a water phase. I cross the line by epsilon and everything abruptly crosses into gas. This is called a type 1 phase transition. Type 1 phase transition, the change of the system is very abrupt and very sudden. There is additional type that is termed type 2. Type 2 says that here on this borderline there is a mixture of a lot of phases together. Okay? So if we look closely, this is my system. At the phase transition, there can be a situation that I described previously, everybody in one phase and they abruptly change to another phase. But there can be a situation that here we have gas and here we have water. Okay. Here we have again gas and here we have water. Okay. So there is going to be a mosaic composition of all this system which is composed on bubbles of phases. Part of those bubbles are going to be liquid phase. Part of these bubbles are going to be gaseous state. Okay? So let's continue this on and on and on and on. And it covers the whole system.
Where do you see this kind of thing?
Oh, in everyday life, you don't see them. They are peculiar, but they are wonderful and very interesting. So the Nobel Prize in Statistical Mechanics in '73 was by explanation of this phase 2, type 2 phase transitions. You see them a lot in magnetic systems. Okay? Don't worry, we will discuss those systems towards the end of the class. But you have to have a very specific temperature and very specific pressure in order to see this. Usually what you see is a type 1 phase transition. Now interestingly for this system, you can say, well, Stas, what you're describing here is almost a homogeneous mixture of two phases, right? And for those two phases, well, maybe you won't have a jump in the density. And this is true. So for the type 2 phase transitions, they are also termed a second order phase transition. There is no jump in entropy and there is no jump in density. Why? Because everything is mixed together, right? If previously there was a jump from one state, one phase to another, here there is a continuous transformation. What actually will jump? If we'll take a second derivative, we will see this later, a second derivative of the chemical potential, it will be discontinuous. Right? So the first order phase transitions are the regular phase transition that you see. Everything changes abruptly. Okay? The second order phase transition, everything changes smoothly, but it's still inside the presence of those different clusters of phases mixed up together. It can be described not by the first order derivatives, by the second order derivatives. So on this plot, we will see that the mu is very smooth. And you don't see this some sort of a discontinuity because it appears only on the level of the second derivatives, second order derivatives. Okay, so what else do I want to say about it? Now, when we look on the phases, so we know, so that let's assume that we have only one type of molecule, so we're describing liquid or gas. Now we can plot T and P as a function of temperature. And we know that at the coexistent line over here, the chemical potential of those two phases is equals to one another. Okay? So mu of gas of T and P equals to the mu of liquid of T and P. Now look on this equation over here. This equation, okay, it is describing this coexistent line. So for the coexistent line, from this equation we can obtain something that is relating T and P, right? We can forget about mu and we say from this equation P is some function of T, okay, and we can plot it down, plot it up. And this function that we obtained from this equation is the coexistent line. Coexistence line. We are simply now plotting it in two dimensions. Okay? Here we will have liquid, liquid. And here we will have gas. And exactly on this line, if you can calculate it from this equation over here, exactly on this line, a phase transition occurs. Now you can say, Stas, I know that there are actually three phases of matter, at least simple matter. We can have gas, we can have liquid, we can have solid. Is there a coexistence? So we can have a coexistence between liquid and gas. We probably can have coexistence between liquid and solid. We know that if we cool down the system, it eventually will become ice. So can we plot on one axis of P and T the three phases? Yeah, sure we can. Sure we can. Okay. Now, what is describing the coexistent positions when all three phases are sitting together? A point, okay? Triple point, okay? So basically what we will have for this coexistent line, again, how it's obtained, is obtained from considering the equivalences of the chemical potentials. So we'll have something like this. We will have liquid, we will have gas, and we will have solid. Solid in the left? Okay, right. It's on the left. Solid. Here we have liquid. Thank you. How do I know there is only a point? Okay, the lines will cross each other.
Cross
Okay, so you're basically, your argument, you have a coexistent line between solid and gas, you should have a coexistent line between liquid and gas, and the two of those lines can cross only in one point.
And then the question is whether there is a firm line between solid and liquid, and whether there is...
So there is no question. How do I know it? So I know that the coexistent line of gas and liquid is satisfied by this equation, right? I also know that there is additional equation that is a coexistence of a liquid, okay, and, for example, a solid, mu, S, T, and P. All of those Okay, and I have all of those equations, so I have 2 degrees of freedom. Each equation decreases the number of degrees of freedom that I have. I started with 2 degrees of freedom. The first equation decreases only to 1 degree of freedom. This is why we have a one-dimensional line over here. Okay, coexistent line. Because we are using only one condition. When we are using 2 conditions, so there is a coexistence between gas and liquid and solid. Okay, so we had 2 degrees of freedom. We subtracted the number of equations that we had. It's 2, right? And we obtained that we have something which is 0-dimensional. What is something that is 0-dimensional? A point. Okay, there are other topological structures with 0 dimensions, but for us it's only a point. Okay? This is why when we're looking on 3 phases, we can only say, well, we have a coexistence triple point, a single one, not many. It's based on this scaling analysis. In general, there is something which is called, and I won't prove it to you because the proof is dull and long, is the Gibbs phase rule. What is the Gibbs phase rule? The dimensionality of the coexistence object, okay, depends on what? It is 2 plus r minus eta. R, number of different types of molecules, and eta, or it's nu, it's ni, right? Ni, yep. Number of coexistent phases. Okay? This is the Gibbs phase rule that one can use in order to understand what is an F dimensionality. Dimensionality. So in order to determine what is the dimensionality of the coexistence object, right, we only need to count the number of different variables that we have in our system. That's it. So we know that there is a coexistence line or a point or a manifold if we're having a lot of different molecules and a lot of different phases, right? Now let's first concentrate on the simple liquid and gas question. And I want to determine the shape of this line, right? I said to you, well, it's determined by the properties of this chemical potential, but I want to exactly calculate how it looks. Okay? How can I determine the shape of this guy? Okay? So we are going to describe the mathematical form of the coexistent line. So what do we know if we have P and we have T? Okay. And the only thing that we know that there is a separation between the 2 phases. The separation we call a coexistent line. And we want to obtain a formula that will describe it to us. Something. Okay. So what we know about this line? So we know that on any point on this line, mu of phase A, alpha, okay, let's not constrain ourselves to liquid, gas, solid, etc. We will have phase alpha and phase beta. So chemical potential of phase alpha at temperature T and pressure P equals to the chemical potential of phase beta for the same temperature, right? and for the same pressure, because we know that the temperatures for a coexistence of two systems together, or two phases, are exactly the same, as we know from stability criteria. Okay? The same happens for pressures. Okay, what else do we know about the chemical potentials? We want to obtain an equation, so I remind to you that we had this gibbs-duhem equation. Okay? d mu equals minus s. I use it as small s. Okay? It's the entropy divided by the number of moles, dt, plus small v, okay, which is a density for us. It's a volume divided by the number of moles, dp. Okay. Now, if we are on this line and we're making a small step from this point to that point, okay, what happens? We know that the chemical potential is changing as what? There is a small change in chemical potential. The chemical potential is changing as minus S alpha if we're on the alpha phase and on the beta phase. So we have minus S alpha dt plus V alpha dp, okay, and it equals to what? It equals to whatever happens on, it's also blue, to whatever happens on the beta phase. Okay? There is also a small change over here. Here we can have that it is minus S beta dt plus V beta dp. Okay. Now let's rearrange everything. Okay, so what we have? We will have V alpha minus V beta multiplied by dt equals to S alpha minus S beta multiplied by dt. Okay. And we can obtain that dp by dt. I can use all the definitions of the derivatives using limits, etc., but for me it's already a derivative. dp to dt equals to S alpha minus S beta divided by V alpha minus V beta. Okay. So this coexistence line is only for first order or also for second order phase transition? It's only for the first order phase transition, how I see it, because for the second order phase transitions the specific volumes are exactly the same and this equation is not defined. Okay. This equation determines what is the shape of this coexistence line over here. It has a name. It's named Clapeyron equation. Right? And by using this equation, if we know what is the entropy in phase alpha, what is the entropy on phase beta, what is the jump in the volume, we can determine what is the shape for each temperature, okay, and for each pressure. We can determine the shape of the line because this is a simple first order differential equation. Okay, so I'm stopping here, and what we will do next week, we will still have some material to cover for this phase transitions, okay, and we will use the additional stability criteria that I have written on this board, specifically how pressure behaves with volume. And we will hopefully we'll end this thermodynamic part next week. Thank you.